We will explore what data can reveal when left to its own devices. We will focus on unsupervised learning, specifically the k-means algorithm, and how to profile the resulting clusters. Find out what the data confessions are. We are now at episode 49 of the course. Having built a strong foundation in feature spaces and unsupervised learning, today we move beyond labeled data to ask if the data itself contains distinct shapes or structures. After 11 episodes of supervised learning, where we mapped features to known answers, we now face a different challenge. Marketing doesn't always have labels. They ask if there are natural types within the data. This is our new goal: discovering structure. In this video, we will cover three main objectives: understanding the nature of the unsupervised contract, mastering the k-means two-step dance, and learning how to choose the number of clusters honestly through profiling. In supervised learning, you have a clear scoreboard with labels, grades, and confusion matrices. In unsupervised learning, there is no scoreboard. Instead, the ultimate measure of success is usefulness and whether your findings lead to better business decisions. Clustering can sometimes be described as astrology with linear algebra if it doesn't lead to actionable results. To avoid this, we hold ourselves to a strict standard. Every cluster must correspond to a distinct, meaningful business action. Remember that every customer is represented as a point in an n-dimensional feature space. While our previous work with cosine similarity helped us find similar pairs, today we are using that same geometric foundation to identify entire natural families. Standardization remains non-negotiable. Without it, features with larger scales, like currency, will dominate the distance calculation. To ensure every feature contributes equally to our understanding of behavior, we must always apply zero-mean unit variance scaling before fitting our model. The k-means algorithm is a simple, iterative process. It involves four key stages: initializing the centers, assigning points to the nearest center, updating the center to the mean of its assigned points, and repeating this process until the groups stabilize. In the assignment step, we calculate the Euclidean distance from each data point to every cluster center. Each point then snaps to its closest center. Think of it as placing magnets on a map. Naturally, neighborhoods form around them. Once points are assigned, we move each center to the average position of its assigned members. This move to middle step tightens the cluster. Because each iteration reduces total inertia, the algorithm is guaranteed to converge. Watch how the centers transition. Initially placed randomly, they walk toward their respective groups over a few iterations. By about the fifth iteration, the centers stabilize into their natural neighborhoods, and the families are firmly established. Implementing k-means in scikit-learn is straightforward, requiring only a few lines of code to standardize the data, fit the model, and obtain labels. Remember, these output labels are just integers. Their true value comes from your subsequent profiling. Choosing the number of clusters, k, is an important subjective decision. Since the data won't provide the answer, we use the elbow heuristic as a tool to balance cluster tightness against the need for a manageable, actionable number of segments. Inertia measures the sum of squared distances to the nearest cluster center, serving as a proxy for compactness. By plotting inertia against different values of k, we look for an elbow where the decrease in inertia slows, guiding our choice for the number of clusters. When reading the elbow plot, look for where adding another cluster stops providing significant tightness. This bend is your starting point. However, remember that the elbow is a heuristic, not a law. Sometimes the data doesn't offer a clean answer because it simply isn't there. If you are torn between two possible values for k, do not overthink the plot. Instead, run both segmentations. Build a profile table for each and ask, does the extra cluster produce a group with a distinct, actionable persona? The algorithm serves the decision, not the other way around. Cluster IDs are just placeholders. To turn them into personas, use the group by operation to profile the average customer in each segment. By reading these averages aloud, you can give each row a narrative name, which is the necessary first step to crafting a strategy. Once you profile the clusters, you can name them. Examples include high-value regulars who deserve loyalty rewards, new and promising customers ready for onboarding, one-and-done bargain hunters, or fading whales who require a personal retention call. Remarkably, these fading whales often emerge organically from the geometry. You might have found them using manual rules in an earlier module, but here, the data confesses this segment on its own, without any prior domain intuition injected. This reveals a full circle moment. In Module 2, we used brittle, handwritten rules to find these customers. Now, we use geometry alone to identify them from raw data. The machine finds what matters by recognizing structural relationships in the feature space. The true test of a successful clustering is whether each persona earns a distinct action. If two clusters lead to the same decision, they aren't actually different. The goal is 4 clusters, 4 distinct plays, ensuring every segment is actionable. If every persona receives the same marketing campaign, the segmentation has no real value. A useful structure demands a unique resource allocation for each group, a different message, channel, or timeline. That is how you distinguish science from mere decoration. Clustering is just astrology if it doesn't change a single business decision. To practice science, we must interrogate each cluster by asking what we would do differently for that group. If the answer is nothing, it's not a cluster, it's just a label. Since we lack ground truth in unsupervised learning, how do we validate our results? We use proxies like silhouette scores, but ultimately, the gold standard is A/B testing our personas to see if they respond uniquely to targeted outreach. Be aware of k-means limitations. It assumes spherical clusters of roughly equal size and variance. It is also sensitive to random initialization and outliers. Always visualize your data and clean extreme outliers before you begin to ensure the results are robust. You can even implement k-means by hand. At its heart, it is just calculating distance, assigning labels, and updating centers to the mean. Seeing this loop in code helps demystify the process. Once you understand the machinery, you can trust the output. To visualize high-dimensional data, we reduce it to 2D using PCA or t-SNE. Remember, compute in n dimensions, but draw in 2D. If the projected groups are well separated, it is an encouraging sign, but use these plots for communication, not scientific proof. Looking back, we see the course arc, from rule-based hunting in Module 2 to vector math in Module 3, and finally, using profiling muscle to interpret clusters today. We have moved from prediction to uncovering latent structure. This moment of rediscovery is the soul of this episode. When you see your machine-learned clusters align with your intuition about customer behavior, pause and let it land. You have successfully taught the computer to see the structure of your data. Now let's get hands-on with your segmentation notebook. You will standardize and fit your customer data, use the elbow method to choose an optimal K, and then profile these clusters using group by to create clear, actionable personas. For a stretch goal, try implementing k-means from scratch using only NumPy. By building the 2-step dance of assigning labels and moving centers, you will gain a deeper understanding of the geometry behind the algorithm before comparing your results to scikit-learn. Remember these key takeaways. Without a scoreboard, your primary metric is usefulness. K-means is a simple but powerful iterative process, and your ultimate success lies in naming distinct personas that each trigger a unique, measurable business action. Finally, we connect these personas to our upcoming capstone. You will use your churn model from episode 10 to identify risk, then apply these new personas to build tailored retention playbooks, shifting from simple prediction to strategic response. We have covered a lot of ground in Module 5. In our next and final episode, we will assemble everything we have learned to ship our churn model into production. I look forward to wrapping up this journey with you then. This program was brought to you by the Series of Thoughts team and Technovative AI.